In 1954, two brand-new Comet jet airliners mysteriously exploded mid-flight, killing everyone aboard. Investigators discovered the cause: square windows. A simple geometric choice, sharp 90-degree corners, created stress concentrations that literally tore aircraft apart at 35,000 feet. Here's why every modern aircraft window is oval-shaped, and the tragic engineering lesson that changed aviation forever, where understanding stress concentration physics became the difference between life and death. The Havilland Comet entered service in 1952 as the world's first commercial jet airliner, representing a magnificent leap in aviation technology. Passengers marveled at smooth, high-altitude flight above weather, crossing continents at unprecedented speeds. Then disaster struck. On January 10, 1954, BOAC Flight 781 disintegrated over the Mediterranean Sea, killing all 35 aboard. Investigators found no clear cause. On April 8, 1954, South African Airways Flight 2000 suffered identical catastrophic failure near Naples, killing 21 people. Two identical mysterious explosions suggested fundamental design flaws rather than random accidents. The subsequent investigation became one of aviation's most important forensic engineering studies, ultimately revealing that window shape, specifically square corners, created stress concentrations that caused metal fatigue and catastrophic structural failure. Materials under pressure develop internal stresses distributed across their structure. In uniform shapes like cylinders or spheres, stress distributes evenly. However, geometric discontinuities, corners, holes, notches, concentrate stress at specific points, creating localized forces many times higher than average stress levels. The Comet's square windows featured sharp 90-degree corners where stress concentrated dramatically. Pressure differential between cabin 8 psi higher than outside created enormous forces on the fuselage. At square corners, stress concentration factors reached 3 to 4x normal levels, meaning corners experience stress 3 to 4 times higher than the surrounding fuselage. Every pressurization cycle, takeoff and landing, flexed the fuselage, subjecting window corners to repeated stress. Over thousands of cycles, microscopic cracks initiated at high-stress corner points. These cracks propagated slowly through the aluminum structure until suddenly reaching critical length, causing catastrophic failure. Stress concentration factor Kt depends on geometry. Sharp corners create infinite theoretical stress concentration. Real materials have finite strength, but corner stress concentration factors of 3 to 4 meant corners experienced forces exceeding aluminum's fatigue strength, inevitably leading to crack formation and propagation. Modern aircraft use oval or rounded rectangle windows specifically to eliminate stress concentration problems. Oval shapes have no sharp corners where stress can concentrate. The gradual curvature distributes pressure forces smoothly around the window perimeter, eliminating localized high stress points that cause crack initiation. Properly designed oval windows reduce stress concentration factors to approximately 2.0 or less, half the concentration of square corners. This dramatic reduction extends structural fatigue life from thousands of cycles to millions, essentially eliminating windows as fatigue crack sources. Post-Comet, aviation regulations mandate minimum corner radii for all fuselage cutouts. Windows must feature generous radius curves, typically 0.5 to 1.0 inches, ensuring stress concentration remains within safe limits throughout aircraft operational life. Modern aircraft undergo extensive fatigue testing where fuselage sections experience 2 to 3 times expected lifetime pressurization cycles. Oval windows show no crack initiation even after equivalent of 60,000 plus flight cycles, minus proof that proper geometry eliminates the Comet's fatal flaw. Aircraft windows use 3 acrylic panes, creating redundant pressure barriers. The outer pane bears primary structural load. Middle pane provides backup, and inner pane with breather hole protects the middle pane from cabin moisture while equalizing pressure. Windows use stretched acrylic rather than glass for superior crack resistance and lighter weight. Acrylic maintains transparency and strength across temperature ranges from -60 ff outside to 70 ff inside, while offering better impact resistance than glass. Outer window surfaces feature hard coatings preventing scratches from airborne particles, hail, and cleaning operations. These coatings maintain optical clarity throughout aircraft operational life despite harsh environmental exposure. Windows incorporate electrical heating elements preventing ice formation and condensation. These ultra-thin conductive films maintain window temperatures above freezing while remaining virtually invisible, ensuring clear visibility in all weather conditions. At cruising altitude, cabin pressure exceeds outside pressure by approximately 8 psi. This differential creates outward forces exceeding 1,000 pounds per square foot. Every window experiences thousands of pounds of force pushing outward. Window frames integrate with fuselage structure through carefully designed mounting systems that distribute window forces into surrounding structure. These frames use multiple fasteners, creating load paths that prevent any single failure point from causing catastrophic window loss. Windows are designed with 2 to 3x safety margins, meaning they can withstand 2 to 3 times normal operational pressure before failure. This provides enormous safety buffer, accounting for material degradation, unexpected pressure spikes, and manufacturing variations. In worst-case scenarios where window failure occurs, aircraft can safely descend to breathable altitude within minutes while maintaining controlled flight. Cabin pressure loss, while dramatic, doesn't threaten aircraft structural integrity beyond the local window area. Boeing 787 windows incorporate revolutionary electrochromic dimming technology. Rather than mechanical shades, 787 windows use electrochromic glass that darkens or lightens electronically at passenger or crew command. This technology allows infinite adjustment from completely clear to very dark, providing superior light control. Windows contain special gel layers that change opacity when electrical voltage is applied. Passengers can adjust dimming level via button controls, while flight attendants can control all windows centrally for cabin lighting management during meal service or sleeping periods. Oval geometry optimization enabled 787 designers to create 30% larger windows than previous aircraft, improving passenger experience and cabin ambiance while maintaining structural integrity through proper stress distribution. Electrochromic dimming eliminates shade mechanisms that fail, provides better light control than traditional shades, reduces cabin heat gain, and creates more modern, sophisticated cabin atmosphere, improving passenger satisfaction. Aircraft windows must maintain optical clarity equivalent to prescription eyeglasses, with minimal distortion across entire pane surface. Manufacturing processes control thickness variations to within 0.001 inches, ensuring consistent optical properties. Acrylic panes undergo controlled heating and cooling cycles, removing internal stresses that could cause optical distortion or crack propagation. This annealing process ensures windows remain stress-free throughout their operational life. Every window undergoes optical inspection, dimensional verification, and pressure testing before installation. Manufacturers test samples to destruction, verifying actual strength exceeds design requirements with appropriate safety margins. Window installation follows precise procedures ensuring proper sealing, correct torque on fasteners, and appropriate alignment with fuselage curvature. Maintenance inspections regularly verify window condition, checking for scratches, cracks, or seal degradation. Future windows might incorporate display capabilities, projecting flight information, entertainment content, or enhanced reality overlays onto window surfaces, transforming windows into interactive displays. Advanced materials research explores transparent aluminum and sapphire alternatives, offering superior strength, enabling larger windows or reduced weight, while maintaining current window area and safety. Nanotechnology coatings under development can repair minor scratches automatically, maintaining optical clarity throughout aircraft life without manual intervention or replacement. Advanced electrochromic systems might allow selective dimming, keeping horizon view clear while blocking overhead sun, or creating privacy between passengers while maintaining forward visibility. Aircraft window evolution represents aviation safety culture at its finest, learning from tragedy to implement engineering solutions preventing future disasters. The Comet disasters taught engineers that geometric details matter profoundly in structures subjected to repeated stress, that corner radii aren't aesthetic choices but critical safety features, and that thorough testing must verify designs before lives depend on them. Every oval window on every modern aircraft represents this lesson, a visible reminder that engineering isn't just about making things work, but understanding why they fail, and designing to eliminate failure modes before they occur. The next time you look through an aircraft window, remember those smooth, rounded corners represent hard-won engineering knowledge paid for with lives lost but honored through designs that ensure such tragedies never repeat.